So let us first discuss the reasoning that will have this situation or this condition that the joint probability will be a product of individual probabilities, and also the first condition that f of Vx is an even function of Vx, and we asserted that it will be something like Vx square. So if we write it together, so the probability distribution will be something like e to the power minus plus or minus Vx square. Why? Or V square. Why? The reason it goes as like this. So we know that V square is Vx square plus Vy square plus Vz square. So you can say that f of this quantity, f of Vx into f of Vy into f of Vz, it will be nothing but e to the power plus or minus Vx square into e to the power plus or minus Vy square into e to the power plus or minus Vz square. Because if you add all of them, either plus or minus, which you do not know yet, so then I'll get if I take the plus sign, it will be Vx square plus Vy square plus Vz square, which will be nothing but V square. And that makes sense because this probability, f of Vx into Vy Vz, has to be the probability of having this velocity component along x is Vx and simultaneously along y is Vy, along z is Vz, which means we are calculating some V where V square is equal to V square x square plus Vy square plus Vz square, and that we directly get from this argument. Now whether the plus sign will be correct or the minus sign. Now if you can think that if I take the plus sign, so at very large velocities, so this will this distribution will blow up. So when V goes to infinity, it will be very high. So that is very highly unlikely. So this plus sign cannot be possible. However, if V or say any of those velocities, say right now let us talk about only the velocities, if the Vx can go to plus minus infinity, but if I retain the minus sign, then either it goes to minus infinity or plus infinity. That will basically, if I take the minus sign, then e to the power plus or minus infinity squared will be 0. So it will probability of having the molecule with extremely high or extremely high speed in either the direction will be very low. So just by logic, we'll say that f of Vx will have a form of e to the power minus Vx square, but of course there will be some constant. We're just writing this arbitrary constant as b Vx square. And also there will be some other constant because we are just keeping this as an arbitrary constant which we can evaluate later. So the functional form of f of Vx will be nothing but a into e to the power minus b Vx square. And so similarly f of Vy will be a into e to the power minus b Vy square, because this a and b are just arbitrary constant and which are independent of the direction. It is just the functional form. It doesn't matter whether it is x, y or z. So if it is fx, the corresponding term will be Vx. If it is fy, it will be Vy. If it is fz, it will be Vz. So we can now say, so what will be the f of v? F of v will be nothing but the product of f of Vx into f of Vy into f of Vz. So I'll have something like a cube into e to the power minus b, and then all these Vx square, Vy square and Vz square will add up. So that will give me e to the power minus bv square. So that is the functional form that we are getting for the velocity distribution, for the speed distribution. And it just we just got it from the velocity distribution, and also arguing that f of Vy will also be e to the power minus bvx square. Sorry, it will be Vy, and similarly for f of Vz. And all these three is giving me this speed distribution. Now the question is, what is this? It is a distribution function, of course, and we are going to evaluate it. What is the evaluation? But before that, let us consider that usually when you evaluate it, you have to integrate the f of v dv. That should be equal to 1, because this is a probability distribution, and since this is a speed, speed cannot be positive or negative. It will be from 0 to infinity. However, we have to now calculate dv in terms of dvx, dvy, dvz, which means, what is dv or f of v dv? F of v dv means it is basically the probability of finding a molecule, which is basically the number of molecules divided by the total number, which you can also say the fraction of molecules instead of probability of finding a molecule between speed range v to v plus dv. But what the functional form we got from f of vx, if we just ask this similar question, what is f of vx dvx, that basically tells you it is the probability of finding a molecule with an x component speed vx to vx plus dvx. So all we have to do right now is to ask this question, how we can get from a dvx, so the joint probability will be nothing but, if you ask this question, that what is the joint probability? Joint probability will be of having a molecule from speed velocity vx to vx plus dvx in x direction, simultaneously the y component velocity from vy to vy plus dvy, and simultaneously the z component velocity as from vz to vz plus dvz. That will be nothing but f of vx into f of vy into f of vz into dvx dvy dvz. Now the first part we already calculated, it will be nothing but f of v. But this is not how to calculate basically this and connect it to the dv, because dv is independent of direction, whereas dvx, dvy, dvz have some direction. Now to give you a better feeling of what I'm saying is that let us consider just a two-dimensional distribution. Suppose the molecules are moving on a plane, and so we can actually draw it in a Cartesian coordinate, and suppose this axis tells me the vx and this axis is for vy. So I only have two components of velocities, and suppose at any point the velocity is along this direction. So I can always say that, okay, fine, I can this will be my basically x component projection will be vx, and then I have a range always. So the range is vx to vx plus dvx. So suppose this is dvx, and this is vy plus dvy. So now the question is, if I had taken the number of molecules with this kind of distribution, where the velocity is vx to vx plus dvx, vx to vx plus dvx, and simultaneously vy to vy plus dvy, and then we ask this question from this information, that what is the number of molecules, or the probability of the molecules of having the molecule having the speed in the range v to v plus dv, then that is independent of direction, meaning if I had chosen the velocity along this direction, okay, this number will be the same. Whichever direction you choose the speed, it doesn't matter, because speed is independent of direction. So this quantity, since it is independent of direction, which it means is that what I have to do is that instead of calculating this dvx dvy, what is dvx dvy? Dvx dvy is nothing but the volume element, or the, in this case actually it is the area element, because it's a two-dimensional thing. Now remember that function was f of vx into dvx, and that function was f of vy into dvy. So their joint probability was f of vx into f of vy into dvx dvy. So that is, I have shown here what it is. It is dvx dvy. So that's a small infinitesimal area element in the velocity space. Always remember that this is not a position space. This is a velocity space. Now, however, when I calculate the speed, I only calculate the length of the vector, which is equivalent to v. Now the length of the vector is v here, length of the vector is also v here. Now v to v plus dv means actually this now dv will be independent of any direction, which means we have to calculate this dv as this particular area, this entire area basically, because that area will now correspond to the dv times v. So what I'm trying to say here is that so in the velocity space, if you look at a particular direction, then you can always say that, okay, fine, this vector actually represents the value which is simultaneously having the speed in the x, velocity in the x direction as vx to vx plus dvx, and the y direction will be vy plus dvy. But I am not interested in calculating that. I am interested in calculating the speed independent of the direction. So, and then I say that the speed will be just v into some dv. Now the question is, what is this dv? Now dv means, now it is basically, if I rotate this velocity vector along any direction, keeping the length same, it is the same v everywhere. And since it's a two-dimensional plane, I'll get a basically circle, and around the circle I'll get an annular region, which is now my dv. So dv is not actually dvx dvy. dv is actually dvx dvy, and then you have to integrate this dvx dvy over the entire range independent of the direction. So that is very important. dv is not dvx dvy. You can get dv from dvx dy in a very clever way, but we are we'll just show you in a minute. But there is an alternative way to calculate. How you calculate the dv? Now it is very easy. Now what you are asking is that all you are asking is that you have a circle which has a diameter basically v plus dv. So the area of the circle is nothing but pi r square. So in this case it will be pi v plus dv. And then what I am asking is that what is the area of the inner circle? So then actually I'll get all this annular circle, or the area of the annular circle. So that area will be nothing but, you can easily do it, pi v square. So it is v square plus 2v dv plus dv square minus pi v square. So you can see that this pi v square will cancel. Now this dv square, dv is already a small number, so dv square we can ignore. So the ultimately it will be 2 pi v dv. Now you could easily get it in another way. So the what I'm saying is that if I have a speed which is equivalent to v, and then if I just calculate what is the probability of having the speed in the range v to v plus dv, then this volume element will not be just equivalent to dvx into dvi, because it is now independent of the direction. So this volume element will be nothing but some factor into some factor we have to consider, and that factor will be just we can get it by integrating over this area, fractional area, independent of any direction. So that we showed it in one way, because this is just a two-dimensional thing. So it's a annular area means actually there will be two circles, and if you just take the difference between the area of these two circles, outer minus inner, approximating the making one approximation that dv square is almost 0, then you can easily get it. You could also get it just directly. So what we are saying is the differential element of an circle. So you could directly write, so it will be nothing but a differential area element around the circle. So area is pi v square, so it will be nothing but 2 pi v dv. Okay, this is the same logic actually which we just said earlier. Or you could do it in a very different way, and this different way is that, okay fine, what we are doing is that, fine, we are varying this is basically Vx. We are varying Vx to Vx plus dvx, and we are varying Vy to Vy plus dvy. Now instead of that, what we are saying right now, it will be independent of the direction, which means natural choice could be to use the spherical polar coordinate. Now what is the spherical polar coordinate? Instead of say Vx Vy, we'll write it as the length of the vector, which is v, and then this angle which we call as say phi, and phi can take value from 0 to 2 pi if we just complete a circle, right? So all we need to know is what is the relation between them, how we can write Vx Vy in terms of v and phi, and then all we are going to do is to integrate it over the entire volume and entire area. We'll just vary phi, because this v is not changing. V we are keeping fixed, the length of the vector, because it is a velocity, it is a speed, and which can be resolved into Vx and Vy. But Vx and Vy has a particular direction. So if you choose some other direction, that will be different Vx plus Vy, but the speed is the same. So that's what we are interested to calculate, a speed independent of the direction. So we have to rotate this vector and find what is the area. That's exactly what we are going to do. So now you can ask this question, okay fine, think about it, what is this thing, what is this dv thing? So this is basically, you can think of dv, the small dv, and then you can always say that if what we are going to do is that we are changing Vx to basically Vx plus dvx, and Vy to Vy plus dvy. In the spherical polar sense, you are keeping, remember this v fixed. What you are doing is that you are keeping v fixed, you are basically sweeping phi to phi plus d phi. So now the question is how this small volume element you are generating in the spherical polar sense. So we'll just draw it again. So let us draw it somewhere, maybe here. So what I'm trying to say here is that you had a velocity vector, so you did not change the direction. So it was phi here, and now you have rotated it to phi plus d phi, and you have moved also v to v plus dv we are keeping. Of course you have also changed it to dv, and then you are rotating it by d phi. So you have generated this area. Now the question is, what is this area? Now you can easily figure it out. So if this angle is now d phi. Now if d phi is small, then we can write this entire area as, look at it here. So what is this length? This length is, so basically we are calculating this infinitesimal area, and this length is nothing but v. So if this is v and this angle is d phi, and if d phi is small, then you can approximate that this arc length will be nothing but v into d phi. So that is just following the trigonometry. So what we are getting is nothing but this area, which is in the rectangular Cartesian coordinate. I got it by this, and the area was just dvx times dvy, and that area we can also get by changing v to v plus dv and doing an increment in the phi from phi to phi plus d phi, and that area is nothing but, now this length is dv and this length is v into d phi. So what I'll get is v dv into d phi. So it is basically dv times v into d phi, so that I am writing as v into dv into d phi. Now that is basically the infinitesimal area which we get, but then to make it independent of the direction, what we have to do, we have to take this infinitesimal area and integrate over all the phi's, because we are not changing the v here. V already we said that we little bit increment in v to v plus dv, but now we ask this question, what is the distribution independent of the direction? Because any direction I take the speed distribution, it should be equal. So that annular area, I can get it by integrating this infinitesimal area over the angle for phi going to 0 to phi going to 2 pi, and that will be very straightforward. Integration of d phi is only phi, so you'll get 2 pi v dv. So whichever way you do it, or whichever way you want to visualize it, I'm getting this annular area as 2 pi v dv. Now we can extend it, the same thing, to 3 dimension, because it's not only vx to vx plus dvx or vy to vy plus dvy, it is also vz to vz plus dvz. So which means actually now I'll have 3 variables. We'll see that these 3 variables are actually, we'll actually want to solve it in a rectangular, in all these ways which we have developed for the 2-dimensional case. So in the 3-dimensional case also, we'll see that there exists a very interesting situation which we are going to discuss in the next section.